last lesson we are discussing the motion of a particle in a harmonic oscillator. And since we are in a quantum course, so we are treating this as a quantum object, and this will describe, for example, small fluctuations of two atoms which combine to a molecule, and they are doing a small vibration around their equilibrium position. This problem is defined by some attraction between the two particles, or the spring constant, so to say, and then you have a typical scale which is 1/time, and that is the frequency of the classical oscillations, and this frequency is determined by the strength of the oscillator, essentially by this. This is a parabola, this is the potential, and the second derivative here gives you the constant of the spring, and then the mass together with that give you the frequency of these oscillations. So what we want to discuss a little bit is the time-dependent solution. And I do this very briefly and without going into the full details, because I just want to convey some general messages. And in particular, what I want to do here is actually try to explain to you why the structure of the creation and annihilation operator in a matrix form was what you saw in the previous lesson. So do you remember the creation and annihilation operator? It's a huge matrix, infinite by infinite. Luckily, most of the inputs of this matrix are zeros, but you have above the diagonal, you have some numbers, or below the diagonal. Above the diagonal is when you lower, that is A, and above. Below is when you go up. Yes, below is when you go up, that's the A dagger, and below you go down. So it doesn't matter so much. We will try to give you some intuition why this is correct from classical point of view. Of course, this is not so easy. The truth of the matter is you need to do all the quantum exercise that was done last lesson. But now I know the answer. I can look, does it make sense, yes or no? This is, I'm clever after the result was found, so I can think about it. A priori, I don't think you have to be really smart to do so. So the wave function in position space as a time-dependent function is given by some Cn phi nx e to the minus I Ent over h bar, where phi nx are the eigenfunctions of the Hamiltonian in position space. The energies are the energies of the harmonic oscillator, En h omega n plus half, and here n goes from 0, 1 till infinity. These are the quantum numbers. This is the usual decomposition of the wave function at time t that we had at the beginning of the class. At the beginning of the semester, we then mostly focused what are these wave functions, phi n, the stationary solutions. But if you remember from the beginning, you can decompose the time-dependent solution as a linear combination of these wave functions, which are found from the Hamiltonian, that is h phi n x equal En phi nx. So essentially in our problem, I know everything about these guys. These are these functions that we found 2 lessons ago. These are their mid polynomials multiplied by the Gaussians. You know everything about this function, I hope, in position space. What are these Cn's? To remind you, you all know Cn's depend on the initial conditions. So at time t equals 0, I prepare the system in some state. It can be a stationary state, for example, the ground state, then this will be very trivial. If you start at the ground state, you will remain there forever. It can be a linear combination of all kinds of states. You start at something. So Cn is determined by the initial conditions. What we saw, however, and this solves the time-dependent Schrödinger equation. All this you know. But what did we see previous lesson? We showed that I can present this phi n in some sense as a vector, right? That is, the particle is in the nth energy state. It can be the ground state. So this representation is in position space, but we can present it slightly differently with a notation which is very popular. You'll see it in all the textbooks, and this is Dirac's notation using the Bryan ket. This notation will write the same thing, well, not exactly the same thing. This is a bit more general. Instead of writing the wave function in a position space, I write it psi as a little bit more abstract. Psi can be actually in many different spaces. It can be in position space, in momentum space. It can be actually an infinite vector with entries like we had in previous lesson. And then I'm going to write this as a sum n psi n phi n e to the minus I e n t h bar. So phi n, again, phi n, for example, in previous lesson, that was called the number presentation. In the number presentation, this symbol is number presentation. We had, for example, to be in the ground state, we wrote it like this. Right? This was just the first entry of this infinite vector. This was this object. Now, this is not only a more convenient way of writing things. This is a very specific one where you present the wave function in position space. So actually what you have here, if I want to be strict, I have to multiply by x. Then this will be the wave function in x space. And then this x phi x will be this guy. So what is a wave function? According to these two examples, the wave function, you have a spatial wave function, but essentially what is the center of quantum mechanics is this state function, psi. It's more general. Why is it more general? Because it can be, for example, it can be this vector. It can be when you project it on x, it can be this thing. It can be in momentum space. What does it mean? That the wave function, psi, the state function, that maybe up till today you thought about it as some very clear object that is the density in position space. It's actually a very abstract notion because it's many things. So psi can go, x space, psi can go p space. It can be a vector. It can be many things. So the most basic quantity in quantum physics is not merely a presentation of a field in position space. This means that the wave function is a bit more, or the state function is more abstract that you can imagine by just looking at the space-dependent Schrödinger equation, thinking that, you know, this is a field in x and that's it. It's more general. And that's why people like this notation, because psi is really abstract. Now, you can say, okay, if it's abstract, but it's supposed to be physics, the point of view here is that the wave function, of course, you cannot measure directly. So the most important physical quantity in quantum mechanics is this state function, but it's not measurable directly. It has many representations. And then you go into, depending what you measure, you are interested in different things. So, of course, the spatial presentation is important, because if you want to know where is in statistical, so where is an electron in an atom, you want to think in this way. If you are not so convenient at the beginning with this more abstract notation, then simply think about this as a special case of, you know, phi n f x. This is the same thing, but this is a bit low-level way of thinking. But you can do this. You can think about this. Oh, this thing is the same. This thing is the same. It's not exactly the same, but, you know, if it's easier for you at the beginning, it's okay. You can do that. So this thing also implies that this structure of this leads you to something that we'll soon discuss called Hilbert space, in the sense that if the state function can be represented in many ways, and not as only a function of coordinate x and time t, then it lives in a more abstract space called Hilbert Space. That's the mathematics of Hilbert Space. We will not go exactly in the details, but that's why you will see many textbooks, they say, quantum mechanics lives in a Hilbert space. Hilbert was a mathematician. He defined the space, what's operations in the space, etc., etc. We will touch on this very briefly only. Okay, so now we have these presentations. And just to write things, I can write, for example, IH psi dot. So I'm using this Dirac notation, equals sum Cn phi n. These do not explicitly depend on time. And here I'll have, when I take the derivative here of time, you see what happens. You know this already. I, En, h, and I multiply by IH. So here I'll get En, E minus ENT over h bar, and this is the same as h, the operator h, sum over Cn phi n e to the minus e ENT h bar, or another way, a way to write down the Schrödinger equation is simply like this. It's exactly the same that you know, but now you have here maybe a vector and not necessarily in position. And then similarly, H, which can now be a matrix, and not necessarily something with second derivative, phi n, this is equal En phi n. So not only does the state function have a more general meaning, also H, we saw in previous lesson, can be either a matrix or a differential equation, whatever you want. So this is a small change in notation of the course, or I think you already saw this in the exercise, but you will see this notation all over the place. So what is, for example, Cn? So Cn you can write in the usual way. This is what we already studied as an integral. Phi psi star x0 phi n x dx, and this can be written in a shorthand notation as psi 0. That's the wave function at time 0. So in this language, it is here you see the complex conjugate of this, and the meaning of these brackets is also this integral times phi n. This is Cn. So here you see another reason why you should work with the notation of Dirac, and that is here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 symbols, and here less. So it's simply a way to write things a bit shorthand notation, because we don't like to write these integrals, oh, this is awful. So this is the same thing, it's a shorthand notation. And again, this psi dot, because you are here, you have this star here, actually. Okay, so this is a way of writing things. Now we go a little bit deeper in the specific. This is also general, and essentially it's not specific for the oscillator. Now, let us now think what is, for example, the average position of the particle in the harmonic oscillator. So I want to concentrate on one thing, not the second moment, but actually on the average one. Why do I do that? Because I know the answer. I know how the average of x behaves. Why do I know the answer? Because, without doing anything, because I know that the average position satisfies the Ehrenfest rules. The Ehrenfest rules relate between the averages and classical mechanics. So I know that x dot on average, and this is the quantum average, this is equal to the momentum over m. So this is exactly like velocity, p over m. And then I know that p dot, which is according to Newton, this is the derivative of the momentum, is equal to the force. And the force is m, it's capital M. I change notations all the time, but omega squared m times x average, quantum average. This is simply the well-known spring. If you have a simple spring, a linear spring, these are the classical equations which you know how to solve. The solution is something like this: x a e I omega t plus b e minus I omega t. Now all of you know what is a and b, but I'm lazy, I'm not writing it. A and b are simply given by the initial conditions of the classical motion. What I want to emphasize here, which is something that you of course take for granted because you know everything about the classical oscillator, is that you have in this solution only oscillating terms with one frequency omega. You don't have omega times 2, you don't have omega times 3, you don't have omega times 2.5, just oscillations with a frequency omega. This is of course very trivial in classical mechanics. That's why we call it the frequency of the oscillator. There's one frequency and you have an oscillation. The solutions, for some initial condition, you have this as a function of time, and you have one frequency, and that's omega, that's it. Okay, you know this, right? We will soon show that this has a importance in quantum mechanics for the structure of the annihilation and the operators. So the classical motion is given by this thing, or if you want, in the oscillator, you simply go, oops, you go backward and forward, and you oscillate with the frequency with the period 2 pi over omega, that's it. What is the exact classical quantum solution of this average position? It's the following a little bit long equation. Let's look what is the average position. From quantum point of view. What do I need to do to calculate the average? The average position. I could do the same for the momentum. Also the momentum as a frequency is the same thing, and you'll get the same type of conclusions. Well, this guy is equal to integral psi xt x psi xt dx. Integral from minus infinity to infinity. What is this guy? This guy is given by the solution. So I need to do this integral from minus infinity to infinity, sum over all n, cn, star, because you have here, this is psi star, this is phi n star of x, e to I en t over h bar, x, and here I need to sum cm phi m x, e to the minus e em t h bar, and then I need to integrate over dx. So what I did here, I simply inserted the solution of the Schrödinger equation. It contains all what I said before, all these initial conditions, all this infinite number of coefficients that depend on the initial condition. And then I need to sum two sums till infinity. I have to integrate from minus infinity to infinity. It looks not so pleasant to do this. How is this related to this? We know the answer. It has to give you only one frequency. So we can write this more explicitly for the harmonic oscillator like this. We can write it sum of n, sum of m. Here I'm just taking the summations from 0 to infinity outside. And inside I'll have an integral from minus infinity to infinity, phi n x star, cn star. Let's write explicitly the energy dependence. En over h bar. We add En. So what is En over h bar? It's very simple. It's omega n plus half. The nice thing about this equation is that it does not depend on h bar. This thing doesn't depend on h bar. And this is important. Why is this going to be important? Because also the classical motion does not depend on h bar. So here I have I omega n plus half times x times cm phi m of x exponential. Now I need to write the same but with a minus sign, I omega m plus half dx. Where?
In the exponent.
T.
Both.
Sure. Now in this complicated object there exists a matrix that is saying I'm a matrix. What is the matrix you can see here? It is essentially the representation of the operator x as a matrix, as an operator in a different space. But I can define x and m as integral from minus infinity to infinity phi n, this guy, x times x phi m x dx. And this guy has two indexes, n and m, and that's why this is a matrix. Actually, we have already calculated this matrix. What is this matrix? How does it look like? I'm not going to do the calculation again, but what is x? Okay, soon we'll come back to this. But this is a matrix, and I can also write it in a very more convenient way, phi n x phi m. It's the same way of writing things. This is a bit more general when I want to think about phi n as a raw vector, infinite matrix, infinite vector. This is an infinite, this is essentially, what is this x? It's a linear combination of a and a dagger, for example. So, okay, we have this matrix. Let's go back for the solution. X as a function of average of x as a function of t. It's a sum over n. It's a sum over m. It is, now we want to write this as Cn star, some junk that is not specific in the sense that it depends on the initial condition, Cm star, Cm, and here I have E exponent I omega n minus m t. You see n and m. So you have n minus m. And here I have this matrix x n m. Now I can say something without working too hard on this x and m. I can say something, two things actually. What is the structure of this x and m? How does it look like? I can say it from the point of view of physics by comparing to the classical motion. And I can say it from the point of view of what we studied in previous lesson, from the point of view that I know what is the structure of A and A dagger. So let us do the same thing, but I think maybe you are starting to see the picture. What do I know from classical mechanics? So what do I know here? Well, these guys are very specific to your initial condition. They are something. But what do I know from classical mechanics? I know that this guy from Ehrenfest's theorem is going to be the same as the classical guy. But in the classical guy, in classical mechanics, as we already wrote, the average of x is A, E, I, omega t, plus B, some numbers with the right units, E minus omega t. So what does it mean? Hence, how can this be from physics? How can this be? Only if this matrix X and M has entries just above and below the diagonal. Hence, X and M is equal to something not equal to 0. C and M, X and M not equal to 0 if N is equal to M plus or minus 1, otherwise it's 0. Means that this matrix looks something like, here you have something, I'm not calculating this, but I can if I want to. This is the diagonal, these are 0, 0, 0. The diagonal is 0. Hopefully you all see why. Do you see why? Do you understand why? Because if this would not be the case, what will happen? Let's say 2 rows below the 0, this would be something which is not 0. Then what will I have here? This guy will not be 0, and then I'll have an oscillation whose frequency is 2 omega t. Or if the diagonal would be 0, then what will I get here? N equal M, then I'll get something that is not oscillating. But I know the classical solution is only oscillating. That's why you have here and here only some terms. This is also what we got in the previous lesson. Why? Because what is x? What is this operator x? X is equal to the sum of A and A dagger. Remember, divided by a constant which gives you the right units, M omega 2H bar. So, I very much hope that you remember, but A, when I put it between two states, let's say N and N, so A will lower your state function. So this guy gives you only when, so for example, A phi M phi N, this is equal 0 unless, not equal 0, unless N equals M plus 1. And the opposite for the A dagger. In other words, A and A dagger goes to some matrix that you remember from previous lesson. Just 0, 0. And here you add square root of 1, square root of 1, square root of 2, square root of 2. All the rest are zeros, etc., etc. Square root of 3, square root of 3, square root of 4. And A plus A dagger is exactly x, up to a constant. And that's why now we can go backwards. The reason why we got A and A dagger as some value only above or below the matrix, the diagonal, is simply because the sum of them have to give x, and in the classical world you have only one frequency of this oscillation. If you had two frequencies, if the solution would be Ei omega t, E minus omega t plus e to the power 22 omega t, then you'll have different type of matrices. So now I want you just to go backwards. You start now with the classical picture, and you start to understand why this thing is like this. Of course, this does not explain exactly why you have a square root of 1, square root of 2. This is not the aim of this exercise. Our aim is just to explain the general structure and not the numbers, because for the numbers you need to do a calculation. The calculation was done in a previous lesson. I'm not doing it here. Okay, so this was some motivation, time-dependent Schrödinger equation. And now we have actually finished the oscillator. If you have no questions, we can now go a little bit of some mathematical background of quantum mechanics. So, we want to discuss briefly what is Hilbert space. But I'll do it with an analogy. I'm not going to define it at the beginning very precisely. This is not a mathematical lesson, it's just to give you some intuition what mathematicians care about. So you know this essentially from in a simplified way from high school, that you can represent things in many different ways. We already saw it in quantum mechanics, but for example, I can present a vector in space, and this is the easy way to see space. Let's say three-dimensional space. Everyone knows what is a space, three-dimensional space, but a space is something more general. So a point in three-dimensional space I can present in Cartesian coordinate like a vector. It's a point. I can also present it with a basis. So I can present it with a basis like this, for example, Vx times a unit vector in the x direction plus Vy in the y direction, Vz in the z direction. And everyone understands that these two things, these two objects have the same meaning. I can define the basis by defining, for example, in some coordinate system, I can define a basis, for example, let's say the Cartesian coordinate system. I can say, okay, Ex is something going to be 1, 0, 0. Ey is going to be 0, 1, 0, and Ez is going to be 0, 0, 1. But you also understand that this is just a choice of basis. I mean, I can choose many bases to represent this vector. This doesn't have to be this Cartesian thing. I can have all kinds of linear combinations of these guys, and I can expand the vector in terms of different bases. And the same thing is going to happen in quantum mechanics. What is the difference? The difference is that the way, at least in the usual language, what are the bases in our case? The basis is not these three-dimensional vectors, but something more general, and that is, for example, the wave functions of the solution of the Hamiltonian. They form a basis, and we expand things with it. But it's very similar. This is what I mean by analogy to this, and we have several representations. So the important thing for mathematician, and this is what they prove, I'm not going to prove this, is that there exist possibly many bases, but you can expand your state function with this basis, and there are many bases. And that is the real mathematical difficulty, to show that it is a complete space, and that is okay. So in our case, we have psi is a linear combination of these states. So this forms a basis. So you can think about it as some analogy that you have these vectors in this simple example, 3. So these were like the vectors, and this defines the space, and this is the function. This is like the v here, in some sense of some analogy, where these CNs are like these numbers. These are very specific to some presentation of one point or one thing. But you see more or less the analogy between these things. And again, the difficult things is, let's say you have some function, psi x and t, and you have some basis, which is the solution of the Hamiltonian, h, phi n, e n, phi n, is to prove that any function within the space, for example, here 3-dimensional points. So any function within the space, which we call the Hilbert space, can be expanded by this basis or not. We're not proving it, but we're taking it for granted. But this is what we assume, and this is what we do all the time, that you can expand it, and no matter what is the wave function, as long as it belongs to the space, you can do this expansion, and this is very helpful for us. So in Hilbert space or quantum mechanics, we have a space of wave functions. But these wave functions, if you want it in the position presentation, can be momentum representation, and these can be, as we showed, they can be vectors. The harmonic oscillator. All these, in generality, are this Hilbert space. Everything that goes inside this space is belonging to the Hilbert space. Like every point in 3 dimension goes into this vector in principle by putting some specific numbers. This is the whole space of the spatial space. So here, this contains all these things and generally more. The assumptions that we are using, that is something that you know, is that the space, or space, מרחב, מרחב, מישהו יודע להגיד מרחב באנגלית? לא. אז מה ההבדל בין... אוקיי, call it linear space in the following sense. If phi belongs to the space, so does A can be some number times phi. Actually, this is a bit annoying for a physicist because eventually we are going to focus mainly on normalized functions. So not all the functions you can just multiply by a constant and then still remain, but the Hilbert space, the mathematical space, is defined in such a way that you can always multiply this and by something, and you're still in the space. Like this happens, for example, when you have h phi equal e phi. Then the solution is not determined by some normalization. You can take a solution and then you can multiply it by a constant. It's still h phi equal e phi. It doesn't matter if you multiply by a constant. So for physicists, this is all trivial. We don't even bother so much to say this, but okay, we have a linear space. And Hilbert space is linear when you multiply in a simple way. So here A is a number. It can be a complex number. That's what I mean by this. And another thing that you know about this space, just now we are becoming formal, and that too, if phi and psi, these are not necessarily h phi and psi time dependent. These are two functions in the space, belong to the space. So does for example, phi plus psi. Because I can multiply here by constants because of 1. So if I want to multiply by constant, it's fine, because if phi belongs to the space, also a times phi belongs to the space, and if psi belongs to the case, also b times psi, so I can have here some additional numbers. This is all okay. So this is also what you know with your physical intuition, because essentially this is the superposition principle. And again, if you have a three-dimensional space and you have a point, then you have a point plus a point, v1, v2, v3, and plus v1 tag, v2 tag, v3 tag. You are still in the space in 3 dimensions, so this is kind of trivial for us. Now, we said that we can define an inner product, a multiplication. We need to define, mathematicians like to define what is your space and what is the meaning of multiplication. So, another... Okay, excuse me, this is going to be, this is 1, this is A, and this is B. This is just a definition, what is a linear space. Now, we define an inner product. Like definition of a more or less multiplication, more or less, but it's not a multiplication. So to define the Hilbert space, you need to define an inner product. What is an inner product? It is phi psi in the Dirac notation, which I can represent. This is a general notation. I can represent it in a specific way by phi n x psi x dx. So like you have two vectors in 3 dimensions, so it's a point. So you know how to define a scalar product. v1, v2, v3 multiplied dot. This is something similar, but you need this, and you already saw in quantum mechanics that we many times need to do these calculations. So now that we are formally introducing them again. Because what I'm going to do now, and also the next lesson, is just summarize all quantum mechanics in a formalistic way. Just to say what are the basics again. So you can think about it as some summary, but it's a bit more than that. Or I can think about this, for example, as for a two-state system, for example, I can have here A, B, star, C, D. So this guy is going to be the phi, always with the star. So if I think about this not as an integration over space, but as some vector, and here I have a two-state system. A two-state system will eventually correspond to a spin. So this is also in Hilbert space, so it has only two strings. And here I explain to you what I mean here by this product. In this case, I take A, B things. So when I do this, A times C, A star times C, B star times D, this is a number. A number like this guy is a number. So these guys are numbers, not vectors, not anything. This is the multiplication like the scalar product of that you know about. The other thing is that mathematicians like to do is that we have a norm. That is phi absolute value squared, which is phi exists. You have to state this. That this thing is a number not equal infinity. This means a lot about actually about the wave functions. For example, consider a wave function that decays like some power law. So let's say some guy tells you, I have a wave function in space, for example, and this goes like when x goes to infinity, like a constant. Or x minus infinity, it goes like a constant. This is not legitimate because here phi x gives you infinity, because if the function goes to a constant, then when I do this integral phi star phi dx at large x, this will be a constant, and then the integral will blow up. So we always assume that the norm exists. It's very specific to the norm and not to other things. You could say, okay, maybe phi to the power 20, phi to the power 20, that will converge. But no, the only requirement of convergence is on this norm. Why is this obvious for us? It's trivial, but we have a different language.
There is no infinity, the boundary condition.
It's the boundary conditions, but it's also simply, eventually the physical interpretation of what is a wave function as a probability density. The mathematicians don't care, or Hilbert didn't define this as he didn't interpret what is the wave function. It just says, okay, we need this mathematical thing to define the space. Of course, Hilbert, by the way, was before quantum mechanics. He defined the space before quantum mechanics came in. He didn't know anything about quantum mechanics. This is a space that exists in mathematics. And by the way, Hilbert was one of the greatest mathematicians in the 20th century. I mean, he was competing with Einstein on the formalism of general relativity, and he was maybe a few months after Einstein, he formulated general relativity. But so Einstein and him was in a big race, and Einstein was lucky to beat him because Hilbert was a better mathematician than Einstein, for sure. So it wasn't trivial. But okay, maybe Hilbert missed some insights that I'm sure he did. Okay, so this is property number 3. We can normalize things. 4, we assume that the space, not the space, well, yeah, I guess so. Space is complete. No, I'll just write it as completeness. Space. Completeness. We can find a basis in which every state, what do you mean by every state? Every state that belongs to the Hilbert space, whether it's a vector, whether it's a function, whatever it is. See, here it's a vector. This is what I mean by vector. You can always expand it by writing like this, sum psi n phi n.
Meaning the phi n's span the space?
Yeah. Phi n, you can always find such phi n that span that the space contains all the functions, but each function can be expanded by this basis, which also belong to the Hilbert space, which is the big thing. So the Hilbert space contains everything, like all dots in space, right? It's a huge, gigantic thing, but each state can be expanded by some basis, and both these guys belong to the Hilbert space itself.
So the theorem...
It's not a theorem. I wouldn't call it a theorem. It's a definition of the space. It's a definition of the rules of the game, not of a consequence. So this is what we are doing, in some sense. It's not a theorem. I didn't prove anything. I mean,
So what it says it's that a linear space will be a linear space only if you can find a basis which spans the whole.
No. It means that in quantum mechanics, in Hilbert space notation, we are going to use this assumption that you can expand it into this some basis. That is, if you find states that are not expanded, then they are out of the game, so to say. These are not proof. I'm not proving here anything. I'm just stating what is this Hilbert space. In reality, physicists add many more things. For example, Hilbert space, you can have a function that is not continuous. Yeah, this is not a problem for Hilbert. You know, a wave function that is something 1, then it jumps to 2. This is okay for Hilbert, but not for physicists. So you should be a little bit careful that this is a minimal requirement from the mathematician, but not a maximum requirement from physical reality. This is not physics, this is math. But it's the millennium. Now we can give an example that is already from this definition of the inner product. Now we can start build some simple math. So for example, so this is a property already. If you want, now I can prove this, but I won't call it a theorem because it's so trivial. So it's a property. Property. From here I know, for example, that if I have C phi times D, C psi, for example, C phi, where C and phi and D are some numbers. These numbers can be complex. Then you see from here, then if I multiply this, first of all, I'm allowed to multiply. This is because the space is linear. So you see, what do the mathematicians do? I define this thing. Oh, good. I defined it then. This is a linear space I can multiply. I define this, and then I define already the inner product. Now I can move forward and prove something trivial, which is that this guy is simply equals C star D psi phi. This is a property. We define operators. And what do those operators do? They act on objects which are in the Hilbert space. On all, this operator can act on everything inside this space in principle. This, in other words, in more physical words, say operator A can be represented in different ways. For example, the position operator, we know already, it can be X, but it can be also a matrix. So here it's very general. It just, you have some state function and you have some operator that is acting, and how do you represent things? It's general. So now the property of these operators is also something that we all take for granted. The operators are linear. And what does this mean? It means that if I act on some object, A is some operator acting on phi, which belongs to the Hilbert space, what do you get? This goes to something psi, which simply remains in Hilbert space. So all your operators are leaving you in the space. For example, if I have a wave function phi of x, and I want to define an operator which is divided by phi of x, This is the division. This is an operator. I'm taking the wave function, I'm dividing it by itself. What does this give you? This gives you 1, right? Is this a legitimate operator? No. Because this is not in the Hilbert space, because its norm is infinite. So it's not an L2. L2 means that the integral square of the function, L2 is finite. Yeah, so this is not. So let us write it like this. If I want a phi, let's write it as 1 over phi times phi, not an operator. Acting on Hilbert space, not an operator from our point of view. We don't consider these type of operators. These are bad operators because they don't leave you in the space. Does not leave you in the Hilbert space since 1 times 1 integral from minus infinity to infinity dx, for example, is equal to infinity. There's no norm anymore. See why they define the norm at the beginning? That is a property. The second property of the operators are that the operators are linear. I mean, in the following sense. This is something you know from all the examples you had. The operators are linear, meaning A acting on psi plus phi is A psi plus A phi. You can define an operator. Let's say you have two wave functions, and then let's say you square both of them, right? That's an operation. But our operators, which will correspond to physical objects like position, momentum, energy, whatever, will always be linear. They will one of them is acting on this guy, one of them is acting on this time. You are not going to do anything which breaks this linearity. All the operators in physics are linear operators in this sense. And you know this already. You know because, for example, momentum is minus IH d over dx. Okay, then you act on one function, then you act on the other function. Again, this is formalism. I'm just telling you what you know, but in a more general setting. We can define a multiplication of operators. So A, how do you define it? You define it by acting or multiplication of operators acting on a state function. A times B times psi. What does this mean? You know this. It's A, and I write it like this. B times psi. And this means that you first need to act with B on psi. This is the meaning of these parameters. After you do that, then you act with A. So the order of operations is important, and we already know this because this means that operators are not necessarily commuting. You cannot just switch the order here. First act B on psi, then A. Things must be ordered, and you must take care. Now, we're going to define Hermitian operators. We will not have a break today. I'll just finish this. So, Hermitian operators. If, can you see with this red, or do you want black? Because the black is dying slowly. Yeah, but you see this black. Okay, if psi a phi is equal to a psi phi, A is Hermitian. You know this by example, for example, for momentum. This was many times on the class, but if you now think about psi and phi as some infinite vectors, you know that this means that the definition of the matrix A as an Hermitian matrix. So it's slightly more general. What did you already see? You, for example, for the momentum operator, this is something you saw already. You know that, let us write this in the, this is, I just plug in here A equal phi. Well, this guy, if we go to the old notation in usual space, is psi star. This is the definition of the inner product, psi star, in this presentation of x, p minus I h d over dx, phi of x, dx. Now I do something that I did before, integration by parts, using the boundary conditions that everything on the boundary is going to be 0, which is due to the norm of the wave function, because now we stated the norm is going to be has to be finite, so I can do integration by parts. This is the boundary condition, and then you know what will happen. This guy will go here, yeah, but it will go here with a plus sign. So this guy will be I h d over dx psi star phi dx. But if you think about this a little bit, this is in our new way of writing, and this is the reason why I'm doing this. It's not because you don't know that P is Hermitian. I think you know this, but now let us just see how I write this. This is exactly P times psi phi. It's the same thing. Notice what is the message here. Remember that when I define the inner product, I had here this star. Remember when I do the integral, I have the star. So here I have P, because here I have the star on all of it. So the minus that I have here, when it's on this side, you take the I to the minus I, and then this guy and this guy is the same thing. So you see by this notation that H is Hermitian, but the physics, or you want what you already know, is comes from these simple integrals. Now we can define every operator A has itself a joint operator, sometimes called the Hermitian adjoint. An operator A has a boyfriend or a girlfriend, has its self-adjoint, It's another operator, a dagger. This is the symbol, a dagger, which is of course a legitimate operator. It's linear. All these good properties hold also for a dagger. And how is a dagger defined? A dagger is defined like this. You have phi, a psi. Now I look for some operator, a dagger, phi. Excuse me, here is psi. So this is just a definition, 3 lines for definition. You have some operator, it acts on psi. That means this operator likes to operate to the right. This operator, instead of operating to the right, it comes here and operates from the left. This is the meaning of this operator. So sometimes it's more convenient to, instead of operating on psi, you want to operate on the other guy. For some reason, for example, you would like to do that. And then, generally speaking, A and A dagger are not the same thing, of course. They can be very different. They are two objects, but you can look for this operator. For example, trivial example, for example, let's say A, the operator A, sometimes I'll have this hat, is a number. It can be a complex number. This is a good operator. It has all the linear properties that we were discussing before. This is belonging to the Hilbert space. Everything is fine, and this is also trivial. So what is this guy? So, okay, let us look. Of course, this is a trivial example, A psi. Now I'm looking for a dagger. This should be equal to a dagger. Well, this is maybe not a good word. This has nothing to do with creation and annihilation. If you want to prefer to have some tilde, this is a number. This is a number, possibly complex. Phi psi, but what is this guy? Well, this guy is equal to a star phi psi. So if a dagger is simply a star, the complex conjugate of this will give you the same thing. So this means that the complex conjugate of a dagger is simply a star. If A is a real number, then a dagger is equal A. If A, this number is complex, then the complex conjugate is the self-adjoint operator of A. So in this example, it's trivial. So if A is real, then A is equal A dagger. Generally speaking, it's not equal to A dagger. If A dagger is equal A, we call the operator Hermitian. If A dagger, if the self-adjoint is equal A is Hermitian. This is obvious if you just go back and look at the definition of what is an Hermitian matrix. Hermitian matrix, you see, I took this guy operating on the right, I put it here. This by definition is the same thing. Not all the operators. Generally you'll have an A dagger, but if A dagger is equal A, then okay, then everything is fine. So for example, let us look at one more example. It's also a simple example. So let us say A is the derivative of x without the I. So what do I have here? I have phi d over dx psi. This is equal to A dagger phi. I'm looking for this A dagger. psi. But this guy, I can write in the usual representation if I want. D over dx, psi dx. This is the spatial representation. Then I can write this integration by parts using the boundary condition. This is minus d over dx phi star psi dx. And what does this mean? That means that, so from here, what is a dagger? Minus d over dx. This is actually the reason why in the momentum you need to add this I in order to get rid of this, so to get an Hermitian operator. So in this case we have a dagger equal minus a. And that's why a dagger is non-Hermitian. In physical terms, it means that there are many physical entities in this world, but there's no physical entity related to this operator d over dx. You don't look for that. I mean, of course, you may look for it, but if you'll find one, you'll get a Nobel Prize. I mean, if you believe the physics of quantum mechanics, which I don't know if everyone believes, but assuming that this is correct, then this has no physical meaning in a physical experiment. This operator has no attachment to some physics.
Why does Hermitianity of an operator is a requirement for it to be physical?
Well, there are two things. So as I told you, we are now very formal. We are French mathematicians nearly. So I'm going to state in the next lesson what are the physical assumptions of quantum mechanics. And there is a list. The reason why I do it next lesson is, and this is also in Koentanuji, up till now we studied many things. I told you many nice stories. And not always did you know what are the assumptions and what are the consequences, right? So what you will get in the next lesson, or if you read the Koentanuji, you will see what are the physical assumptions, okay? And one of the physical assumptions is going to be that physical observables, which you know already in many examples, so this is not a big surprise, like momentum, Hamiltonian, orbital angular momentum, spin, which you did not learn, but everything, each observable has an operator which is Hermitian associated with it. That will be an assumption of physics next lesson. Here these are only mathematical assumptions. This is just, we are just preparing the grounds for next lesson in some sense. The other reason, which you will now see, is that Hermitian operators have a property. Maybe you know this from other courses. What are the special property of Hermitian operators? You know? What?
Are always diagonalized.
What do you mean always diagonalized? Well, you can, but that's a mathematical result. There are many objects that you can diagonalize. Hermitian you can diagonalize, right? But more importantly is that their eigenvalues are real. This is the answer to your question, and that is, if you want to associate with physical observables Hermitian matrices, then their eigenvalues have to be real, because another assumption of quantum mechanics would be that the eigenvalues of Hermitian matrices are those values that you can measure in the laboratory. Okay? So let us go through the maths. So yeah, you will have to wait more, but essentially you more or less see where I'm going, I think. This is the physical motivation to define Hermitian operators. Before doing that, let us just play around with the self-adjoint operator. So we had this operator A, not this number that I had before. This was in the previous class. This was this lowering or annihilation operator plus I, P. This is the momentum operator. This is the position operator. For us, they can be presented as a matrix or multiplication, whatever you want. 2mh omega. And now let us look what is A dagger. You know the answer because I wrote it on the board last lesson. But I didn't prove that A dagger is the self-adjoint of A. But how do you do it? Well, I'm now going to do it quickly without multiplying it with some operator here, operator here. I'm just going to take all this m omega 2h, this x bar plus I p 2m h bar omega, take the adjoint. So what will happen when I take the adjoint of this number? This is a number. It's a real number. It's also important. What will happen to this guy? When I take its adjoint, it will stay the same. This is the same that I showed you already. If I multiply by A is Hermitian if A is real. When I multiply this guy, okay, and another point is what is x? So here I get m omega 2h bar. Here I get x bar. What is x bar? The self-adjoint of x. Well, it's very simple, but it's x. Yeah, because all I need to do is you have phi x psi dx is equal to x phi star psi dx. So x, it's the same thing because x is real, right? You're integrating along the real line, and then again, it's not surprising physically because it means that x is a Hermitian operator because you know it's an important operator, okay, but it's not a proof. So here when I take the self-adjoint of I, what do I get? Get minus I. This is because of this inner product definition and this psi. And then I have P dagger and all the rest of the numbers, nothing happens to them, and this is a mistake. It should be square root. And this is what we defined, if you remember. Okay, this, let's write it m omega 2h bar x minus, I'm using the fact that these are Hermitian, 2m h bar omega. So, and this is the definition that you know. This is what I said last lesson, that I just gave them these names. I called this A dagger, but now you see the A dagger is really the self-adjoint of A, and in this example, of course, because of the minus sign, A dagger is not equal to A, and that's why these things, they are important physically. They take you from one level to the upper level or lower you, but they are not associated with physical measurement directly, but they are operators in Hilbert space, and they are super important, of course. Okay, so now we will come to a general statement, and that is and we will do it with our new notation. Yeah, I think you know this, or you should know it from some algebra course, maybe. So a property of Hermitian operators is that, and this is a, okay, this is a theorem. The eigenvalues of Hermitian operators. Doesn't matter if this is a matrix, then you have an eigenvalue. This is something like a derivative, like P, whatever this operator is. And this is the important stuff, are real. It means the following in the Dirac notation: phi n equal En phi n. Here I introduce some quantum number n. It could be also a continuous number, it could be a discrete number, it could be many numbers, but just for the sake of it, think about a one-dimensional thing where you have one quantum number. That's just to simplify it. For example, A could be H. Then AN are the energy levels. These energy levels are real. We saw in a few examples that they are real, but not only. If the operator A is P, then I mean by this is the minus IH d over dx. What are the eigenstates? These are simply, for example, these states, H bar K, EIKX. Let's say you put it in a box so it's normalizable. So you see these are ANs, but they are indexes with a K which is continuous. So, but you see this is real. This is the eigenvalue of P. Let us do it with a discrete type of setting. Simple. So what we will do, we will take phi n, we'll multiply this equation by phi n, A phi n. What is this guy? Well, A phi n, by definition, this is AN phi n phi n. I'm not saying now that this is real or not, I'm just saying this is the answer, right? This is the answer. Because A phi n, this is the same thing as what I wrote here. But it is also Hermitian. If it is Hermitian, I can write it also like this. Phi n, I like the parenthesis, phi n. This is because it's Hermitian. This is an assumption. Not every operator is like this, but Hermitian operators can act, instead of on the right, they can go here. But what is AN phi n here? It's AN star. Because this comes from the definition of the inner product that you had, that you need, for example, in space, the integral from minus infinity to infinity, you need to take this guy like you have here, but you have to take the complex conjugate. This is the definition of the inner product in this thing, and here you are left with phi n, phi n. But this guy has to be equal to this guy. Now this guy is not zero because the norm exists. So this means that AN is equal to AN star, which means AN is real. So it doesn't matter if you have an Hermitian matrix, you have an Hermitian operator, you are assured that the eigenvalues of this operator are going to be real, as we already saw in a few examples. Another theorem is that the eigenstates so the first theorem was on the eigenvalues on these ANs, and now I'm going to discuss some general property of the states themselves, the phi n's, the eigenstates of Hermitian operators. What are they? A nice property. Exactly, are orthogonal. We already saw this several times by the most important example. We solved the Schrödinger equation, the time-independent one. We got the energy levels in the harmonic oscillator. We got the wave functions, and they are orthogonal to one another. We saw it in the particle in the box, but now we claim it's general, and it's because that the Hamiltonian is Hermitian. That's why we got this miracle of orthogonality. So how do you prove this? I'll prove this only for non-degenerate states, like one-dimensional Hamiltonian or only one quantum number, non-degeneracy. So, okay, we know that A phi n is equal to something, A n phi n. We know already that this A n is a real number. So what we're going to do now is we're going to multiply this by phi l. And again, if you don't like this very general symbol, so imagine that this is the integral from minus infinity to infinity, all this junk. This is much more convenient.
Phi l?
Yeah, some L. Some other quantum number. The more general proof, this is not a general proof because I use only one quantum number, but in principle you can have many quantum numbers. So that's why I limit my proof a little bit, but don't worry, let the mathematicians do something. So this guy is equal to an, because A operates on phi n, phi l. But I can also operate on the other side, because it's Hermitian, A phi l, phi n. So this is AL. We know that this AL is real. So it's not AL star. Here I have a mistake. This is L and this is N. Phi L, phi N. So these two guys are the same. So if AN is not equal AL, this is a non-degenerate state. For example, if this A would be the Hamiltonian, what would be the AN and the AL? These would be two different energy levels. So the energy level of the first level is, let's see, in the harmonic oscillator and the first excited state. So if AN and AL are not the same, what did we get? That this guy is equal to the same as this guy. How can this be the same? Only if phi L, phi n is equal 0 for n not equal L. That's it. That means they are orthogonal. So you see that this notation, it's many things. It's both physics of trying to tell you, wow, the wave function is not what you thought about. It's something more general, this psi. But here you see also that this Dirac notation and this definition of this Hilbert space eventually gives you very simple, elegant, few lines proofs of these things. But of course you have to pay some price, and that is you need to learn this language of this Bra and Ket. Yeah? This guy is called Bra, this guy is called Ket. Together they are the brackets. So just to summarize, the eigenvalues of Hermitian operators are real. The eigenfunctions orthogonal. And because we demanded that the norm exists in the Hilbert space, it means that we can normalize them. norm is finite, so the wave functions can be normalized. In the same way, I'm not showing this, but it's trivial and it's nearly the same thing, and you can do it by yourself. If I look at the average of A, and A is Hermitian, A, what is A? Real. It's really trivial. You just need to move the A acting to the right, you move it to the left, and it's the same thing. You take the complex value. So this is another thing that we will continue in next lesson. This is important. This is easy. You should prove it by yourself. If the average of A corresponds to the classical observable, for example, the average position or the average momentum correspond to a classical position, they better be real, right? And this is a property of Hermitian operators. So to conclude all this, Hermitian operators have very nice properties, and that's why in the next lesson we will use them as the basis of the physical introduction to quantum mechanics. So what we had today was just a kind of brief mathematical introduction to some concepts, etc. You need to understand what is a self-adjoint, how to operate with the A, how to move it from the left to the right, all these notations, and then next lesson we will use those notations to just outline what are the physical assumptions behind quantum mechanics, which is the chapter, I think, 3 in Kohen-Tanuji. Okay, so if you have no questions, I wish you a happy Hanukkah and enjoy your life a little bit before the end of the semester. Okay, so goodbye.